So we are starting transmission to YouTube. Yeah, we are already transmitting to YouTube. Perfect. Good. Victor, can you log into YouTube and see if everything is okay?
Yeah, it works.
Okay.
Working. I'm seeing you.
Very good. I think the latency is not great. Wow. That's perfect. It's working.
Eu vou receber um produto aqui e já volto.
Okay. Okay, so we can put down here. Good. Yeah, Bruno, you are live on YouTube now. Wow. So we just need the students to get in. People are getting in. That's great. We have almost 30 students that are active in the course. So we have 14 now, 16. That's good. I was listening that you won't stay for long in Japan. You are leaving Japan soon?
I don't know yet. I mean, for at least one more year I'm here, and I will see how they deal with my contract.
Yeah, and maybe you can come to Brazil and help us with cryomicroscopy. That will be good, really.
Yes, I have some nice feelings about Brazil, so why not?
Yeah, in Senabio we need people like you to help us with the cryo things, and we just gain a budget to buy a microscope from Faye.
I see.
It will be very good when it gets here, and we will need people with your experience to help us. Maybe you can think about that and talk with Kildare, Vanderlei, and then see how things goes. And then
Right. Yeah.
Here is hot the entire year. It's warm and sunny the entire year, so it's really good.
Yeah, I remember. I was quite a number of times in Rio.
Yeah.
Yeah,
It's really good. And
yeah.
then with this COVID situation getting resolved, I think things will come back to normal, and will be much better, because it has been very difficult. And then we have a lot of it's almost I was almost 2 years at home. I didn't get out, and then just for work, just for the lab.
Yeah.
So it's really stressing. It was really stressing.
For us, it was we could go out. It was not the problem, but we were more or less not leaving the island. I mean, we were staying for. I was staying for 1.5 years almost on Okinawa. I had short trip to Japan, but mainly we were on the island.
Yeah, it's complicated.
Yeah.
We did not have this so rigid restriction here in Brazil, because it's difficult to hold Brazilian people at home. It's really difficult to people to understand that they need to stay home, that they need to avoid social interaction. So it was really difficult. But anyway, we are used to have a lot of social interaction, to have contact with people. So it was really difficult. But now it's everything. It's getting better.
Yeah, we were also on those pretty restricted. So this year we went on Sundays or weekends, let's say, every now and then we went for snorkeling, so that we had at least a small group of people who could be together and having some contact, because otherwise only sitting at home in the free time. During the day we were at work, but for the rest, evenings, everything was closed, and so we were just sitting home.
Yeah. I know, I understand. That's really great. Yeah, Bruno, I think it's 9:04, and then I think we can start. What do you think, Victor?
Yeah, we can start now.
We have already 27 students, more or less, and then I think we can start. So we will start, make some announcements to the students in Portuguese, and then we come back to you, okay? So, bom dia, pessoal, tudo bem? Vitor?
Ok, deixa eu começar a gravar. Pode falar, Chuchu. Eu vou começar a gravar aqui.
Ok. Bom dia, gente. Vamos começar hoje nossa terceira aula do curso. Alguns anúncios, né, para vocês. Então, quem ainda tem problemas, né, para acessar lá a plataforma, né, Vitor? Escreve para o Vitor, para ele tentar resolver. Pessoal que vai fazer a disciplina o curso como disciplina também, mandar os dados para o Vitor, para ele poder fazer o registro. E a gente estava conversando com o Bruno como que ele preferia, né, que fosse feita a interação com vocês. E ele falou que prefere que vocês parem, né, durante a apresentação e façam perguntas de vocês mesmos, né? Então, ele quer que vocês participem, façam perguntas, e pode, né, abrir o microfone, falar durante a apresentação, fazer as perguntas. Quem não quiser falar em inglês, né, fazer as perguntas em inglês, tiver, né, com vergonha e tal, me sentir muito confiante, escreve aqui no chat, em português mesmo, e a gente passa a pergunta para o Bruno, tá bom? O importante é vocês participarem, né, e a gente ter uma aula, assim, interativa, né, de troca de conhecimento, tá bom, gente? Então, eu vou começar a aula fazendo uma introdução sobre o Bruno, tá? Só um minutinho. Aqui. Ok. Estou toda atrapalhada com esse zoom aqui.
Achou?
Achei. Okay, so good morning, everyone. Welcome to the second day of the course of advanced topics in electron microscopy. And today we have a pleasure to have here with us this morning, Dr. Bruno Humbel. Well, Dr. Bruno Humbel has made his doctorate in cell biology at the Federal Institute of Technology in Zurich, Switzerland, and Pos-Doc in cell biology at the Max Planck Institute for Biochemistry in Germany. He worked as assistant professor in molecular biology and as associated professor in molecular cell biology at Utrecht University in Netherlands. He was head of the Facility of Electron Microscopy at the University of Lausanne, Switzerland, that I have a pleasure to know in my stay there a long time ago. He now is leader of the imaging section at the Okinawa Institute of Science and Technology Graduate University in Japan. So Dr. Bruno Humbel has focused his work on biological sample preparation for optimal imaging in the electron microscope. So among his expertises are preparation methods based on cryofixation, free substitution, freeze fracture, but also he has worked on correlative light and electron microscopy techniques. And nowadays, I think he's working more on the development of a Fixation tomography field, right, Bruno? So you can speak a little bit more about your journey if you want. So I would like to thank you again. And it's very, very good to see you. And it's a pleasure to have you here with us. Thank you.
Okay, yeah, thank you, Carolina and Victor, for inviting me to this meeting. As I said before, actually, I would love to be in Brazil now, to be on stage with you. But okay, the situation is such, at least that we on distance can still connect, which is also somehow wonderful. So, shall I start?
Yes, please, you can start.
Okay.
Can you share the presentation?
Okay.
Yeah.
Okay, that's just a view from close by where I'm living. It's almost like Buzios. It's really good area. So yeah, I will talk about correlative light and electron microscopy. But I understand this is a course that people already have quite some knowledge about electron microscopy. But still, I hope you will excuse me for that. I will, in the beginning, tell quite a lot about chemical fixation because I realize that we are all doing it, and few of us really know what we are doing. So I hope this can be helpful for designing your experiments in the future. So, but first, as we have correlative light and electron microscopy, which probably is these three kind of approaches that you have: live observation in the light microscope, and then you correlate it with, of course, then the dead prepared sample at high resolution. Or you use it as an overview, the light microscope as an overview to see find your cell of interest in tissue, for instance, and then you can analyze it at high resolution. And I also would like to show you that one of my aims is also to use light microscopy to improve label efficiency. I will not, wait a minute, I need to. All is visible. Okay. I will not talk about the live observation, and this is simply because I don't have experience in it. So in fact, there is much more in correlative microscopy that I'm going to tell you. I restrict to the areas where I have some experience in. So I hope, again, you apologize for not covering the whole field. Correlative microscopy is actually already old. I want to show you this slide here, which I was looking at the time when it was more or less in the beginning of my career, when I was looking at cytoskeletons. There was this work from Webster et al., where they were looking at the cytoskeleton of a cell in the fluorescence microscope, and then continued the preparation, and we're looking at the same cell then in the electron microscope. So going to the light microscope, you know, there is Ernst Abbe was one of the physicists who worked on the optics for light microscopy. And he found this famous formula that the distance between 2 points for the resolution of the light microscope is the distance d is dependent on the wavelength of the light you're using divided by this factor, which makes more or less that the distance is in the range of the wavelength, or half of the wavelength. So if you have 400 nanometer, let's say UV light, then you can go down to about 200 nanometer of resolution. And with exception of the new technologies of super resolution microscopy, you cannot lower you cannot get to higher resolutions with a light microscope. But there was then in 1949 or earlier that the Broglie found that if you have fast moving particles, that they also have wave properties. And with this, he gave electron microscopy a chance. Here is the formula where you can see that the wavelength for an electron microscope is quite a simple equation finally. It's 1.5 factor divided by the acceleration voltage, and then you take the square root out of it to get the wavelength. So if you look at it, then we see that the wavelength in an electron microscope, the electrons, is really quite low. So in fact, you should be able to see individual atoms because you're much lower in the resolution. And as we see now with the new methodologies and new approaches they are having in cryo-electron microscopy, like better cameras for recording single electrons, correctors for the spherical aberrations, and so forth, we get close to atomic resolution, but we don't get down to the wavelength resolution which we would expect in accordance to what we have heard about the light microscope. So anyhow, with modern cryo-electron microscopy technology, single particle analysis, we can go, I think we are now with the apoferritin on 1.2 or 1.3 angstrom, but normally if you look at the different proteins, you can very often go below the 3 angstrom resolution. But anyhow, we are handling with different problems at the moment. We are working with room temperature samples, so with chemically fixed samples, and these are the preparation steps you are taking: chemical fixation, dehydration, and resin embedding. Oh, by the way, I would like to mention, so please, if you have any questions, just interrupt, raise your hands, or meaning ask the question directly to me, or if you prefer, you can also write your questions in Portuguese in the chat, or also ask them directly in Portuguese, and Carolina or Victor will translate it for me. So please ask during the talk, because that makes the talk much more interactive, and that can, let's say, better focus on what you really want to know. With having said this, I continue with the chemical fixation. So why are we using it? We use it to prepare, to protect the ultrastructure from collapse and also from loss of cellular components. As you know, we will see in the further steps, we go through pretty unhappy surroundings for the cell, and that we can do that, we need to stabilize the structure first. So there are different agents we are using for cross-linking proteins. We can use aldehydes. For lipids, we can use urinal acetate or osmium. Urinal, by the way, I will be mentioning later on, is also a fixative for nucleic acid. And of course, this will have an influence of the protein structure. They can change the protein structure. And if you do immunolabeling, what's also a name for doing a correlative microscopy is, it can happen that you mask your epitope and you cannot find it anymore. Now to formaldehyde, which is probably the most used fixative, especially also for light microscopy. So as also glutaraldehyde, the aldehydes, they react with NH2 groups, with amino groups on proteins. That's why they cross-link proteins also. And formaldehyde is a very small molecule, as we'll see in a moment, so it is quite fast in its action, but it has the disadvantage that cross-linking is reversible. That means when you take out the sample from formaldehyde, put it in buffer, then formaldehyde will detach from the amino groups again. And it's even worse, formaldehyde actually is a gas. So if you keep the container open, formaldehyde will evaporate and the fixation will be reversed. And thanks to the, let's say, not so good fixation of formaldehyde, it has less influence on antigenicity. So that's why it is actually very preferred, because with formaldehyde, most of the cases, you still can get very nice immunolabeling. Now we're coming to one of my worries. Everybody talks about they are fixing with paraformaldehyde. And I tell you, no, you're not. It's impossible, because paraformaldehyde is these huge molecules. So these chains times 90, that makes 20, that makes about 100 molecules of this structure. That is paraformaldehyde, and you buy it as paraformaldehyde as a powder. And with that, you don't fix, it's a powder. If you want to fix, you depolymerize it, usually with at higher temperature, with sodium hydroxide. There are also other methods. So if you are patient, you can also, in a closed container, you can steer it overnight, and then it will also dissolve. But this is the usual recipe, that you use some temperature and sodium hydroxide to dissolve it. And then you get formaldehyde. As I said, this is the gas formaldehyde. And together with water, it makes this methane diol. And this is then the molecule that is binding to the amino groups in the proteins and making the cross-linking. It's very nicely described in this paper from Kiernan. Also, he still mentions paraformaldehyde, but I really try to fight against this expression, because that's not the molecule that fixes. Now, coming to glutaraldehyde, Gareth Griffiths, also a very famous person in the field, called it once the queen of fixatives, because since the introduction glutaraldehyde by Sabatini, something in the early 60s. It is the fixative of choice for biological samples. Aldehyde, it fixes NH2. With this, it cross-links proteins. It's a big molecule, you will see later on, so it has a slower penetration. But for us, it has the huge advantage. Once it has fixed, the fixation is irreversible. And why? I will show you. It can have, because it's an excellent fixative, so it can have a big influence on the antigenicity, so on the immunolabeling. And this is, in my opinion, predominantly because it really fixes the cellular components, the proteins, so well that you lose not so many proteins. That means if you have an isolated antigen you make an antibody against, then this antigen or this protein actually is not a single protein in your cell, but it's surrounded by partners. And if you fix that partner to the protein, then the antibody cannot see the epitope anymore. So that's why people don't like to use high concentrations of glutaraldehyde. Now we're coming to the glutaraldehyde. At low pH, it's pentamer, as you see, 1, 2, 3, 4, 5 C groups. And on both sides, there is the aldehyde, the double bond oxygen. And with the NH2 group, it can form the so-called Schiff base, and then you will get this structure here. This is reversible, as it is for formaldehyde, as you see here with the double indicated arrows. But we are using glutaraldehyde at higher pH, so usually we are doing fixation at pH above 7. So some people use 7.2, others use 7.4. So in that pH range, and if you're looking in that pH range, then for glutaraldehyde doesn't exist as a single molecule, but it dimerizes, and I have read in papers it can even form up to a pentamer. And now what we're seeing here, we have the, pardon?
Sorry, Rodrigo has a question.
Yes?
Rodrigo, do you want to speak?
Yes, Bruno, sorry to interrupt your talk, but I was taught that sometimes in fixation, you can have like a mix with paraformaldehyde with glutar. And I was taught that this was because the paraformaldehyde enters more rapidly on the cell, and glutar, it's more a little bit bigger molecule. You recommend this type of fixation, like the mixing with paraformaldehyde with glutaraldehyde?
As I said to you, I recommend the mixture between formaldehyde and glutaraldehyde. Paraformaldehyde will not help you in anything.
Sorry, I tried not to use this word.
It's a fight for which I will never ever win, but I try. Don't worry, I know what you mean. No, actually, as you will see a little later, in many cases, it's useful to use formaldehyde together with glutaraldehyde. So let's say whatever, 2%, 4% formaldehyde and less glutaraldehyde. This also, especially if you want to do fluorescence, will give you the possibility that you have less autofluorescence, because now we're coming actually back to this molecule where I was. If we have here an oxygen double bond to this C group, a single bond, and then another double bond. This is a mesomeric system, and this system can give autofluorescence. Actually, if you look at fluorescent antibodies, they are full of this double bond, single bond, double bond. They give you the fluorescence. And if you do what you said, if you use formaldehyde together with glutaraldehyde, you have a faster penetration of formaldehyde, let's say more or less stabilizing the structure, and then the glutaraldehyde comes and really fixes it.
Okay, thank you.
And yeah, and if you stay, in my experience, something like below 0.1% of glutaraldehyde, then you don't suffer from autofluorescence. You still can get very nice fluorescent images, I mean, positive fluorescent images.
Okay, thank you.
You're welcome. Okay, so we have now, as I said, at higher pH, we have the dimers or even up to pentamers, and they react then completely different, not completely, the Schiff base is the same. But now if we have the Schiff base, as you see here, it is stabilized by this mesomeric system, because the electrons at this point, they don't know anymore where they really are. They are traveling between here and over this whole area. And this is the effect of stabilizing the reaction. And that's one of the reasons why glutaraldehyde at higher pH, I mean, we would say the ones we are using, 7274, is irreversible. Okay, a lot about glutaraldehyde. Here, just to show you, actually, to come back, the knowledge I built up or the readings I did on all these fixatives were because in the lab of Martin Müller, where I did my PhD, we were very much discouraged, or let's say not allowed to use chemical fixatives, because we were a cryo lab. We did cryofixation, and then at a certain moment we started with free substitution. Free substitution we started in the beginning already, but at the later stage, where especially during my thesis, we were then also using low temperature embedding. So more or less in our lab, fixatives were taboo. And then to, let's say, justify my thesis, I had to read all these fixation papers to know why we didn't want to have it. And this again is a very nice picture actually from my colleague Hans-Rudi Ebersold, the first author here. He was the representative in Martin's lab from microbiology. And as he was not allowed to use fixatives, he was doing cryofixation of the bacteria and then free substitution, epoxy embedding. And then his colleagues from microbiology said to him, but why don't you have mesosomes? Everybody's publishing about mesosomes. And then Hans-Rudi got a little bit worried. And so he thought, okay, let's do chemical fixation and then cryofixation. So after chemical fixation, he found also the mesosomes. And this was the picture he usually had. And with this, he could prove that this membrane vesiculation, especially at areas like we have it here, where a new membrane is synthesized and is not yet stabilized, this vesiculation is due to the fixation. So that means it's a fixation artifact. And then we, much later at the Utrecht University, we happened to come to the project from Jean-Luc Murk, where he was looking on the endocytic pathway. And he wanted to do tomography, and for this decided to do cryofixation. And then, as you see here, we have high pressure frozen free substituted endosomes here, early endosomes, late endosomes, and lysosome. And then we thought, why not try to do a glutaraldehyde fixation first, and then cryofixation and so forth. And that's what we did in the upper row over here. And then we see that the early endosomes and late endosomes, due to the chemical fixation step, they shrink. And you see it much nicer actually if you look at it in 3D. So while after cryofixation, the free substitution, the early endosome looks nicely turquoiscent. After chemical fixation, it looks more like a flat backpipe. So again, you see that the chemical fixation can have an influence, but to my opinion, we need to know that this is happening so that we know to which level we can interpret our results. So we shouldn't, if we want to look at clearly defined membrane-membrane interaction, then probably we should use cryofixation. If you just want to look at the general distribution of whatever mitochondria or so in a cell, then it's good enough if you look at chemical fixation. As you will see, if you go into volume microscopy, most of it is done with chemical fixation. And still you can get valuable information. Just another slide to show you the influence of glutaraldehyde on immunolabeling. And this slide is actually very nice in my opinion, because it shows you there is a tendency, the more glutaraldehyde you're using, the less well you can label your protein. But the amount of reduction, it's completely dependent on your antigen, actually on your epitope. So you cannot really predict if I use 2% glutaraldehyde, I cannot label anymore. It really depends on the system you are working with. But for this, it's important to know there is a tendency. So that's why you rather prefer not to use high concentrations of glutaraldehyde if you intend to do an immunolabeling afterwards. And as we just discussed before, if you go to 0.01, then you're somewhere in here, then you are in the upper part of this special graph. Now we come to osmiums. Actually, I'm exceeding now a little bit, because osmium you don't really want to use if you want to do correlative microscopy. But why? Probably these slides can explain to you. So osmium reacts to CC double bonds, as you see over here. With this, it could cross-link proteins or mainly unsaturated fatty acids. What I will show you, actually the downside of osmium is that if you use it at room temperature, it reacts as a protease. For the fixation, it has a fast penetration, and it's really destroying quite a lot of immunolabeling. It doesn't completely abolish it. Again, we shouldn't take it as a dogma you are not allowed to use. But it's in tendency, osmium is not very good if you prefer to do, if you want to do an immunolabeling. Again, here, very nice work from done by Jacques Dubochet, also ages ago, in '83. He was looking at another type of bacteria. And also there he saw these mesosome structures, or over here. So what he did was he osmium fixed those bacteria, and to prove it afterwards he made native cryosection. So that means he osmium fixed the cells, then cryofixed them, and then cut them with a cryo-ultramicrotome and did cryo-electromicroscopic imaging. And if he didn't do the osmium step, he didn't have mesosomes. So again, be careful, or be aware of, maybe not careful, but be aware of, if you treat your samples with chemicals, then you will change somehow their morphology. And that's just to keep up, to know what you're looking at finally, how to interpret what you're looking at. And now we come to the protease effect. On the left side, we have filamentous tubulin, actin, And if you treat it with osmium, then you will see the right side, so we'll get small pieces. Actually, far more or far clearer, it's actually demonstrated in this picture here by a colleague of mine at Utrecht University, Wally Müller. He followed the so-called Tanaka protocol. Tanaka was a professor at Tottori University here in Japan. And he was specialist on scanning microscopy. He was also collaborating with Hitachi in improving scanning microscopy, making high resolution scanning microscopes. I heard, you heard yesterday about those scanning microscopes. So as a scanning microscopist, he wanted to look into cells. And as my colleague Wally did, he had a filamentous fungi. He froze it in liquid nitrogen, then he smashed them into pieces with a hammer, put the pieces out of the nitrogen, and put them into osmium tetroxide solution. And he repeated and repeated the step of osmium tetroxide several times. And then what you see is you can very nicely look into the cell. I mean, they're cut open by hammering them frozen. And then you lose your cytoplasm. Here the cytoplasm is gone. You just retain mitochondria, you retain some debris within the nucleus, the nuclear membrane. Of course, you see the cellular membranes very nicely. Here we have ER, multivesicular bodies, vacuole, and so forth. So actually, osmium cuts your proteins into pieces, you wash them away, and then you have a very nice look at your cell structure in scanning microscope. And more modern image is this one from Koga. I forgot where he comes from. I thought he's coming from Hokkaido, but I'm not sure anymore. Who was making Tokuyasu cryosections. And then he treated Tokuyasu cryosections with osmium tetroxide. And then he got this nice structure of in brown ER, in green Golgi apparatuses, and in blue here the mitochondria. I mean, as you see, the picture is really aesthetic and can give you quite some interesting information about membranous structures within the cell, but your proteins are gone. They are chopped into pieces and washed away, so be aware of that too. Now, urinal acetate. Urinal acetate binds to phosphate groups with which it can fix nucleic acids and, of course, phospholipids. And there is also quite a nice paper from Bernard, as you see, very old. If you stain your cells with urinal acetate and then remove urinal with EDTA, which is a chelator, then it can remove the urinal from almost everything, so especially from DNA, but not from RNA. With this, you can make a very nice RNA stain in electron microscopy in your cells. So you can see how the RNA is distributed in your nucleus, for instance. And that's how it works. Urinal acetate is complexed by the acetate. So urinal here is complexed by acetate. And then the acetate is released, and then to this oxygen, the phosphate can bind from lipids, and if you have two, like you see over here, then you can use it as a fixative. This is also the reason why you shouldn't use urinal acetate. You should use urinal acetate in water. Don't use it in a buffer, because if you go higher, urinal is probably something like pH 4, maybe 4.5. If you go higher, you have hydroxyl ions and the hydroxyl ions can complex instead of phosphate, and then your urinal acetate will precipitate, also with other ions. Just a little overview to show you the less fixative you're using, the less strong fixative, for instance, here glutaraldehyde you're using, the higher your chance for getting a nice immunolabeling. And then another word about buffers. All the labs, or not all anymore, but somehow cacodylate has come into electron microscopy. I still don't know why. I'm looking, and if anybody of you has a paper where it says why cacodylate is used, so it must be a paper in the 60s or earlier, why cacodylate was used in electron microscopy, please send it to me. I'm still looking for that paper. I didn't find it. But cacodylate is not a good buffer. As you see here, the pK is 6.2 and the pH range is between 5 and 7.2. Actually, it's at the edge where we are using it, and there are even people who are completely scrupulously using it at pH 7.4, where it doesn't buffer anymore. So it's not only useless buffer, but it's also poisonous. It's not good for your environment. It contains arsenic. So why not just drop it and use, let's say, phosphate instead? So for routine work, we use phosphate. If we are really trying to give more care to our cells, then we use a more adapted buffer like HEPAs. You know that if you have cell culture cells, you grow them in HEPAs buffer very often. So it's, let's say, cell-friendly or cell-accepted. And please do not use Tris. Also, Tris belongs to the same buffers, to the so-called good buffers. But Tris, as I will show you a little later, does react with glutaraldehyde. So first coming, yes?
You said that cacodylate is not a good buffer, but
yes.
I grew up in the microscopy area, and we use cacodylate for everything in electron microscopy. Why do you think that you use as a routine the cacodylate buffer? But we learned here that the phosphate buffer do not maintain the pH very well, and so the cacodylate do this. Why do you think that you continue to use the cacodylate buffer instead of phosphate?
I don't know. I mean, phosphate is 100 millimolar. Maybe that's not strong enough for keeping the buffering if you think so. I mean, you can of course measure, you can check it, but if you are worried about the buffer capacity, then use HEPAs. As you will see later in a further slide, I think we use HEPAs at 200 millimolar, and that's an extreme good buffer, and it buffers in the range you want to have it buffering, and cacodylate does not. So anyhow, in my lab, cacodylate is banned. There is no cacodylate in my lab anymore. So we use, as I said, for standard, we use 100 millimolar phosphate. Or if we are really concerned about the buffering, then we use HEPAs. And here's
so do you use HEPs in your lab?
Pardon?
Do you use HEPs in your lab as routine buffer?
Phosphate buffer we use as routine.
For electron microscopy, okay.
Yes, yes.
Rodrigo has a question.
Yes.
Rodrigo.
Hi, I have an intruder here, sorry. So Bruno,
yes.
About the cacodylate situation, I guess that I have some hypotheses, because one of them is that we are taught here to use like the Karnofsky solution.
Yes.
Which is iode. And the other thing is that I think cacodylate has arsenic, right?
Yes.
So the phosphate buffer is more likely to get fungi or something. And
That's true. That's really true. But I mean, you shouldn't get things old. So you should use.
Yeah, of course. Yeah. I get your point.
Yeah, that's certainly true. I mean, but this, I mean, there are a few arguments. Some arguments say it doesn't precipitate with phosphate can make precipitates, whereas cacodylates does not. That's probably also true, but I never had really problems about it.
Okay.
And Hepus doesn't make it. But I think people very often use cacodylate also afterwards together with osmium.
Yes.
And for osmium, actually, I don't buffer anymore. I use osmium in water.
Okay.
Yeah. And here on this slide, that's one I found, as you see, in actually my friend Heinz Schwarz found it in a book, because he still could find this book, which was lucky. It's a Bulletin de Société Chimie Biologique, so it's all in French, as you see, Tampon Cacodylate de Sodium from Blumel. And this is the graph of the buffering capacity from his book. And there you see that 7.2, it's finished. And he was using cacodylate because he was working in biochemistry with phosphatases. And there, of course, you couldn't use phosphate buffer because it's the substrate of phosphatases. So that's the only thing I found up to now about cacodylate. So I'm happy to share.
Thanks.
Welcome. And now we're coming to the tris, why we cannot use tris. As you see here, tris has NH2 group, and this reacts with glutaraldehyde. So if you have time, if you feel interested, take a volume of tris and take a volume of glutaraldehyde, and then you will see it gets yellowish milky because it reacts with each other. So don't use tris. Hepus is fine, pipes is fine, but not tris. So here now we are coming to the question of Rodrigo also. So we have fixatives for immunolabeling can be different concentrations of formaldehyde. Actually, this year I was using for a difficult to fix sample for dictyostelium, and then I went up to 8% because there is a paper from Bachon where he showed that if you have formaldehyde at the concentrations higher than 4%, then it also fixes well, then it also fixes irreversible. But formaldehyde has a very, very high osmotic activity. So I think 2% is or so is already close to 1,000 milliosmol. And our blood is in the range of 300. So that's why you see here the steps 1, 2, 4, 8. So I was going stepwise up. If I went directly into 8%, my nice cell like this was just making like this. It was completely flat, so it was not useful. And then we have more or less my favorite fixative is in this range here, 1%, 2% formaldehyde and 0.01% to maybe 0.2% of glutaraldehyde. And then this fixative formaldehyde together with picric acid buffered. This is a very fast working fixative also. So if you have cells that are difficult to fix, then you can use this. It was introduced by Zamponi to fix sperms, and I was then using it for the for dictyostelium because dictyostelium somehow could close the membrane. So, for instance, if you put it into 1% of glutaraldehyde, the surface was immediately fixed, but inside the vesicles were still moving around for a very long time, so the structure looked horrible usually. But with fast fixatives like this one and with formaldehyde, I finally got nice images. And then here the fixatives. Yeah.
Sorry. Well, I have a question about
Sure.
the use of picric acid, because I read that picric acid is not good for the immunogenicity, to keep the immunogenicity, although they can improve membrane contrast. So what can you say about that?
Sorry, which urinal?
No, the picric acid. The use
Oh,
of picric acid.
no, actually, picric acid was very good for immunolabeling. So I've first used the Bouin solution of picric acid, which is in light microscopy, because my colleague had excellent fluorescent images.
Wow.
And his fluorescent images were just wonderful. And my electron microscopical gold label was horrible. And then I was using the Bouin solution, and I got nice immunolabeling, but there was nothing left of the cell, only the cell membrane. And then by accident, when I was traveling in the former East Germany, I went into a bookstore and found a very nice book in which this recipe was described, and that saved my time in Munich. Because with this I finally could work with good structural preservation and good immunoreactivity.
Great. So thank you.
Yeah.
Perfect. Thank you, Bruno.
No, welcome. You please always interrupt. So, and let's say fixatives here are nice. These are nice buffers. So either 200 millimolar HEPAs or 100 millimolar of pipes. And then my colleagues at the University Hospital in Utrecht, they used the so-called FEM buffer, which is pipes, HEPAs, EGTA, and magnesium chloride. They didn't know why they were using it. I mean, why this buffer exists. Of course, they were knowing why they were using it, because it's a very nice buffer, and with results in good morphology of the cells. But I was recalled that I've seen this buffer before. Namely, it's from Manfred Schliever, who was using it for the cytoskeleton preparation. So that went back to my PhD almost, when I was doing cytoskeleton preparations. And the EGTA in there, of course, these are the buffers, but the EGTA in there is to remove calcium, because it binds calcium. And calcium, if bound to alpha-actinin. Alpha-actinin doesn't cross-link actin anymore, and bound to actin-severing proteins. Actin is chopped into pieces. So that's why he used EGTA to remove calcium, so that the cytoskeleton is stabilized, and then to give a counter ion back. As calcium is removed, he added magnesium. So that's how this buffer came about. It's a little history, but maybe it's interesting for you. Now, dehydration is to infiltrate the samples with the apolar resins. We can do it with ethanol or acetone. We are usually using acetone nowadays. And here again, one of the cacodylate stuff, namely people use cacodylate, also use propylene oxide. And I have banned that also in my lab, because it's also not very healthy. And it helps actually to remove cellular structure. The structure, if you look at the propylene oxide treated cells, they look much clearer, much sharper but this is because some of the structural elements, they are missing. So that's why you have a much clearer image. Okay, yeah, so they can remove, they can denature proteins. So chemists use actually acetone to precipitate proteins in thin solutions if they want to make Western blots and so forth. And of course, it can dissolve lipids. Now, during dehydration, that's also, as you see, all these data are very old, but probably still true. During the dehydration, you have volume changes of your samples. So in the first instance, you will have somehow an expansion of the volume. And then reaching once in the range of 70%, then you're back to 100, and afterwards you will have serious shrinkage of your sample. And this is because you remove the water. You need to have the water to keep the integrity of your proteins. And once you remove it, then the structure will collapse, let's say shrink. It's not completely collapsed. And here we have a comparison in somehow in volumes. All this is done by Alan Boyd. And freeze-dried sample, I always like to compare it or to argue it might be similar in free substitution, that we have more carefully removed water, and maybe we can even not remove all the water because the structural water usually is quite tightly bound and can only get away at higher temperatures. So with this, we hope that, or we argue that one of the reasons why free substitution structures usually look better. Yeah, here we are with free substitution, just to show you also what is happening during the substitution. And that's also why I think we should, for, let's say, well-preserved samples, we should use cryofixation and free substitution if we cannot use cryofixation and cryo-electron microscopy imaging of the cryosection. So here you see, first we will have at low temperature, we will have a dehydration. And if you are lucky, then this dehydration is taking place below the devitrification point of the water. That means before the water becomes hexagonal ice. Then we raise temperature, maybe stepwise. Let's do it stepwise to -60. And then there are some publication indicating that osmium tetroxide will start fixing at -70. And the interesting thing actually is on osmium, there it fixes as we see it in the diagram I was showing you. Then osmium gets from oxidation state 8 to 6. So that would be in the fixation configuration. But at room temperature, osmium is predominantly in oxidation state 3 and 4. So it's not the one that fixes. So with this and hints, we have never really seriously proven it. The point is that if you use osmium fixation in free substitution, then it doesn't destroy your epitopes. Then you can even use it for immunolabeling. Anyhow, let's go further. Glutaraldehyde fixes at higher temperature, but if you want to have a real good glutaraldehyde fixation, you need to go above 0 degree. So here it starts, but some proteins will not be well fixed. There is a paper of Monaghan saying that histones are not fixed at that low temperature. Okay, now embedding. Let me see how far we are. Oh, good in time. So embedding, we need embedding that we can section. And there are different resins. There are the epoxy resins, which is Ippon, Araldite, Spurs, Durcopan, and so forth. We have metacrylates like Lovicryl, London resins, and Unicryl. I think you cannot buy it anymore. I wanted to remove it, but I didn't remove it from this slide, I realize. And then very nice embedding actually is embedding in ice, which is the Tokiyasu technique, where you embed in a sucrose water mixture. So it's not really ice, it's a high concentration of sucrose in water. Now, during the infiltration with the resin, we have the same problem as with the organic solvents, because these resins, monomers, are even more organic, more anhydrous, yeah, more organic than the acetone or even ethanol. So again, we have denaturing and dissolutions of the proteins, and then during polymerization, we can have covalent binding to the epitopes, as I will show you in the next slide, next slide. So here, epoxy resin, we can have the covalent reaction with our molecules, which you will see later on can be very, very beneficial. We have nice sectioning quality, smooth surface, and with this all probably due to the covalent binding, probably to the smooth surface, you don't have very much topology. We have a reduced immunolabeling capacity, and epoxy are very nice fixative. Now we come to the slide. As the dogma says, if you want to do immunolabeling, you have to use weak fixatives, and you have to use metacrylates. So that's what my colleague Lianjun Wang did. He was from Nijmegen University. Here we have a piece of pituitary gland, which was high pressure frozen, free substituted in 1% glutaraldehyde, and then HM20 embedded. And he was looking for neurotransmitters in the pituitary gland. So he did a lot of experiments which were quite successful, but then he came to this mesotoxin. You see the structure below. And he couldn't label it. He was completely desperate. And then I said to him, please send me the amino acid sequence, which we have down here. And at that time, I didn't have this molecule, I just had this one. And I said to him, you only have one terminal amino group. Forget it, you cannot fix it. It's too small, and with this amino group, it will not work. I knew from a group in Zurich, if they wanted to label GABA, they were using 6 or even more % of glutaraldehyde to get it fixed. So I said to him, listen, let's change the tactic. We don't use HM20, we don't use metacrylate, we use epoxy, we use Ippon. Here we are. These holes here were not holes anymore, they were empty, were filled, and they were nicely labeling. So you see, one of the dogmas, don't use Ippon, you're not allowed to use epoxy resin if you want to do immunolabeling, you must use metacrylates. It's not always true. So thanks to the fixation effect of the epoxy, we could keep the mesotoxin in the pituitary gland and show it. Here you see all the amino acids that can react with the epoxy group. And here we have it even clearer shown. It reacts with hydroxyl groups, NH2 groups, and sulfhydryl groups.
Bruno?
Yes?
I use it to perform some immunocytochemistry in epoxy resin here. And
Yes.
when we have some situations, antigen is abundant and not too sensitive, but we treated the epox with oxygen peroxide to do such a permeabilization to facilitate the antibody enter. Do you think it's okay for have a nice immunocytochemistry in epox resin?
I mean, I don't really know what it does, the peroxide. I know that it was used by some people to oxidize the osmium because they thought the osmium was making them problems. But it can be that it also somehow whatever detaches some of these connections here, and this way making the protein more accessible for your antibodies. So I'm really sorry, I don't know enough about that chemistry to answer your question correctly.
But it's okay, thank you.
Welcome. Okay, then we have here here I removed the unicryl. Here we have the metacrylates. They cannot react with the biology. Sectioning is not more difficult, that's a mental problem. It has more rougher surface relief, which allows better allows better access for the antibodies. So we have better antigenicity. And here you see how the reaction works. We have a peroxide, I think. There are different names, I never can keep them apart. There is one that decomposes in heat and the other one that decomposes under UV irradiation, but both of them split in two pieces, in two radicals, which is indicated here in red. And that then starts a radical reaction here. And this propagates then through the metacrylates. And that's how the metacrylate polymerize. And the lovicryls with the LRs, they don't tell us what's in there, but with the lovicryls, we know that we have long chain monomers, and we have also one molecule that organizes cross-linkings. So that's why you get in this almost fish net with which you trap your biology so that you can cut it. And that's also why there is more gaps in between, so the antibodies can better access the epitope. And then we have the technique of Tokuyasu. He was Japanese, working in Singer's lab, as far as I remember. And with my moving to Japan, I also was told that he was a professor at Kurume University, where we had a conference in 18. So, and there we made a special Tokuyasu symposium in his honor. So, yeah, here he embeds in this high concentration of sugar and freezes it. Then you get the macromolecules, they stay in the water. You have cryo-ultramicrotome you need to cut. You will get, as we see later on, a rough surface for giving you really excellent labeling properties. So for immunolabeling, it's, I would say, my favorite method. As you will see later on when we are finally at the correlation. So for instance, for brain, where we cut, we take the brain out of the head, and then cut 300, let's say, micron sections with a vibratome. And when the sections are coming off the blade, we immediately put it in a fixative. With this way, we get, to my opinion, a much better fixation than we get with perfusion fixation. I know you shouldn't tell that to neurobiologists, they will contradict me, and they made us a hell lot of problems to get this paper published, but finally we managed. And I will show you a picture later on. You can also embed your cells in gelatin. So this is a gelatin block, and in the tip were the cells, and then you can cut small cubes. It's just that you can easier handle them. Then you put them on this pin in a cryo-ultramicrotome, like in any other case, make nice pyramid. Then you can take sections, pick them up with freezing sucrose solution. There is also different options for the pickup. And very often first I'm looking at it on a toluidine blue stained sample in the light microscope to know that I have something, my cells are there, so I'm in the tissue. And then I collect the sections, let's say, usually semi-thin sections like 200, maybe 300, not 200 nanometer on a cover slip, and about 100 nanometer I usually collect on the grids. And then we can do parallel labeling for fluorescence. So this is catalase labeled in liver with the fluorescence, and then on the grids we can label it with gold. So that's also already one type of correlation. I mean, it's not really correlation what we address with correlative light and electron microscopy, but it gives you the correlation of the label. So if you don't see in the fluorescence image any label, or if you see lots of background, don't bother to go to the electron microscope, don't bother to do the electron microscopic labeling, because gold, as you will see later on, is much less efficient than fluorescent label. So if you don't see fluorescence, you won't see any gold. If you see a lot of background here, then you will have just black spots everywhere in the electron microscope. So use this correlation to check the quality of your antibody, the quality of your system, and then go to the electron microscope.
Bruno?
Yes.
Yeah, I have a question about the sample preparation for Tokuyasu sections. You said that you embed the sample in sucrose solution.
Yes.
And then after the section. This is only for tissue, or you can do this for cells in suspension.
You can use it. You can also do it for cell suspension. You can use it for everything. So if you use it for single cell suspension, then you best embed it in gelatin so that you can make a block with your cells in it.
Mm-hmm. But you don't fix it previously.
Oh yes, I do. Sorry, sorry if I missed saying that. I mean, this tissue is fixed, and the cells are also fixed. So let's say for many years I was using this 2% formaldehyde, 0.02 glutaraldehyde. Now I use a bit more glutaraldehyde. I'm a little bit more daring. But first you fix, and then you put it into gelatin, and then you impregnate the blocks with sucrose, and then you freeze it on the stop for the cutting.
Okay, perfect. Okay.
Yeah, sorry not having mentioned that.
No problem.
Okay, and here we have the reliefs. So you see EPON is rather smooth, HM20 is a bit more hilly, K4M, especially at the membrane, is really very nicely hilly. And then it looks even more, let's say, rough if you look at the Tokuyasu section. So that was very nice work of Jörg Stierhoff from Tübingen. He made relatively thick Tokuyasu sections, put them on a epoxy block, and then prepare them with, did an immunolabeling on it. Then he fixed it again and embedded it in EPON, and then made cross sections like you see here. So these are cross sections through the cryosection. And then you see the gold is everywhere there where there are holes. You see here, the membrane is split off, it goes here. It's even more or clearer to be seen over here. Or if you have a little hole here, then it goes inside. Or if you have bad fixation, then it can also go inside, as you see over here. So this shows you two things, this slide. First of all, that a well-fixed cryosection also does not allow the gold, at least, but we also have evidence the antibody go into the section. But usually, if you use the Tokuyasu preparation protocol, the fixation is not so very good. So you have much better 3D access. So that's probably why it is so much more successful for immunolabeling than, let's say, resin protocols. Okay, good. Here is the promised image of perfusion fixed brain, where we see the astrocytes as a nicely empty space. And when you use our fixation protocol, then the astrocyte looks like this, completely filled, looks really like a cell. But anyhow, we just have a problem. We have now a project with a neurobiologist, and I was telling him this, and I said, but listen, if you don't want to have problems with publishing, you probably better use perfusion fixation. So we'll see what he's doing. Now we're coming a step further towards the correlation, and this is the reason why we do correlation, because we want to know where the zone of interest is. So if you look at here, pituitary gland of a zebrafish larva, we wanted to label with an antibody against the prolactin. And as you will see later on, this is the area, the magnification, and the area where we could find the, the label. And all over here, there is no label. So with other words, if you look at this grid, if we have no hint, we have to go from one field to the other. We just have to go over at this magnification, as you see here, that we can find the gold particles. Here you see them. That's the gold particles. That was the yellow area. So that's even then, probably now on the screen you can easily see it. If I project it, even then it's difficult to see the gold particles. Anyhow, so the here I labeled them a little bit that you can easier see them. So the problem amounts to finding a few coins in a soccer field. So this was in UK, but that during a course I was losing some money, and then you need something like a light guide to know where you have to look, because otherwise you have to walk up and down the whole field. But if you have some indication where to look, then you can find it down here. So these coins here are in relation to the football field, in the same size as this image to the gold particle. Just to give you a little bit practical part. So one of the correlation we did was, for instance, to take sections from the same block. So let's say a 500 nanometer section first, which then was toluidine blue stained, and then it was in EPON embedded for let's say to make a stable embedding EPON between the microscope slide and the cover slip, and then we could look at it in the bright field microscope to get orientation of the sample. That's what we see here. So this is the toluidine stained sample of an intestine. Then the next section was 50 to maybe 100 nanometers. So as you see, the sections are so thin so that we in principle are still in the same area, even if it's not the same section. And here we did a fluorescent label with primary antibody fluorescent marker, then moviola embedding, and then we looked at the fluorescence. So this gave the impression of actin in green, and I think it was beta-catenin in yellow, and propydium iodide to show the nucleic acid in red. And then next was again a 50 to 100 nanometer thick section, then with gold labeled, and that we could look at in the electron microscope. So here I don't show you the label, I only show you the sequence of sections. So we have one section for toluidine blue overview, we have one section for fluorescence, and then we have the next section for electron microscopy. So that was, let's say, our beginning that this work I've mainly done with Heinz Schwarz in Tübingen. We were, let's say this was Heinzen's beginning in doing correlative microscopy and pulling me into that field too. And then another way of doing correlative microscopy is this one. So we have a fluorescent image. These are yeast cells, if I remember correctly, and we were trying to find yeast cells that were mating. So I had a fluorescent image on my computer and took it to the electron microscope, and then I had the same grid in the electron microscope, and here you see the cells. And so then I was counting from here, this cell I still could recognize down here, and then 3 cells over, and then we come to cell number 11, that's somewhere here, and so forth. So this was another way of doing correlative microscopy, so that you have the fluorescent image and then manually, or how you would call it, do the correlation. And now coming a little bit to instrumentation in between, before we go further with correlative microscopy and instrumentation that can be used for doing correlative microscopy. So this was electron microscope or electron light microscope that was constructed by Akashi. That was a very advanced microscopy company from Japan. Unfortunately, it disappeared, but they had the first super resolution I cannot use because that's reserved for light microscopy, but they had one of the first high resolution scanning microscopes. They had the field emission guns and so on before other companies were even thinking of. And I think part of its knowledge then went into GEL. So these guys, they made both, they made transmission and scanning microscope. By the way, in one of the books Roland Fleck and I were editing on scanning microscope, there's a wonderful article from Mike Hales on Akashi, on the whole history of Akashi, if somebody's interested in. So anyhow, here you see the light microscope image and the electron microscope image for the correlation. That was an instrument that was used in pathology. But for a long time I thought this was the first one, but no. The first one was from 1937 by this group, Martin et al. And they made a light microscope combined to an electron microscope, not because they wanted to do correlative microscopy in our thinking, but with the light microscope, they wanted to prove that what they see in the electron microscope is real, so that they can see the same thing. I mean, it's also correlation, but they wanted to prove that the electron microscope doesn't show you something that doesn't exist. So, yeah. Then, because these slides came later on, this knowledge came later on to us, because we thought that we were really genius when in Utrecht with Hans Gerritsen from physics, we thought about it would be nice to have a light microscope combined to an electron microscope like we see over here. And that was then what Sasha, collaborator from Hans, was constructing. So she made a lens that could be introduced into the pole piece of the electron lens, so a glass lens. And together with FEI, we were developing this. FEI was enabling us to tilt the sample by 90 degrees. So we could take images with the fluorescence here, and then pull the light microscope back, turn the sample into the electron beam, and then do electron imaging. And here are, here that's the setup. So that's the light microscope down here, not this one, this is the cold trap, but down here is the light microscope that Sasha was constructing. And the stage tilted to 90 degrees, and then we tilted back, and then we could do the electron imaging. So here is the comparison of the light image of cells. At that time, Mattia Karman was looking at the cells that were damaged by UV irradiation. So cells that were starting to produce caspase 3 and starting the apoptotic process. And then we labeled for Cliff caspase 3. Here we see the fluorescence of it, and then we could find the same cells back in the electron microscope, and then look at higher magnification, where we discovered these bodies here that were induced by the UV irradiation. We also did a gold label on those bodies, but the gold label was really quite weak and was not let's say, convincingly above background. But with the correlation, we could somehow prove it. And there was another interesting thing we observed, namely that the urinal acetate is quenching fluorescence. So if we use here a different urinal mixtures, that's urinal oxalate, oxalate with urinal acetate. This was a recipe that was originally also introduced by Tokuyasu to stain Tokuyasu sections. And this is then urinal acetate in methylcellulose. So you see more or less, if you can call it, the more stringent you are with urinal, the less fluorescence you are having. And on the other side, the more contrast you're having. So you have to walk the line between fluorescence and contrast. And this is probably also one of the reasons why finally this microscope was not so successful. But there are other companies still using it. So this is the Geol variation that was constructed by Nagayama in Zurich and Okazaki. I was privileged to have sabbatical in his lab, where I actually was working on phase contrast microscopy, not on correlative microscopy. But anyhow, I got he was introducing me to his plans, and I saw the construction of not the plans. I saw the plans of the instrument, but I think Jill never really realized it. Not, pardon? Another microscope that is realized is Secom from Delmic. This is a company in Holland, mainly associated with Delft Technical University. They built a light microscope into a scanning microscope, so the optical path goes through a window from outside. Yeah?
Sorry, I
So
think that
question?
she left her microphone on.
Oh, I see. Oh, I thought it was a question. No problem. So they do light microscopic imaging from below. So there's a cover slip from below, and they can do electron microscopic imaging from the top. It's quite an interesting instrument, and they have a few nice pictures what they are showing. I don't know in how many labs there are, but there's definitely one at Crick in London. Then Chiol came with a similar idea, but they kept the electron microscope in the vacuum and the sample outside, so they can with their instrument, you see here, that's the electron gun, and then they have a nitrate, what is it, silicon nitrate window? I'm not sure anymore. They have a window which allows electrons to pass through, and then they can look at cells in liquid. So you can look at them in a fluorescence from the top and from below with electrons. And a similar idea was done by an Israeli group. They made a shuttle for the correlation. So they have the sample here, look at it in the light microscope, and shuttle it to the air scan. And here again, there is a membrane that separates the air from the vacuum, but lets the electrons go through. So you can look with electrons onto the sample. Anyhow, so this was the different microscopes I was once gathering for a review on correlative microscopy. And I don't know how well they are in use. I mean, I didn't hear of them anymore. I just know that Delmic is still working.
Bruno?
And then, sorry?
I think we have in Semabio a Tech9 Spirit microscope that we can do light microscopy too.
Oh.
It's an objective, 10 times objective, and then we can do some work on that. Although the magnification of the light part is not huge, we can make a correlation with the electrons, the team image. So
I see.
have a microscope there.
Yeah, I mean, to my opinion, you don't need to have a fantastic resolution in the light microscope, because you have the resolution in the electron microscope. The light microscope must tell you where you have to look.
Yeah,
I mean, that's the approach I'm favoring.
Yeah, I think the problem for me is that I work with a tiny cell. It's really small protozoa. So usually my labels are in vesicles inside the cell. They are very, very small.
I see. Yes.
Yeah, I don't think it. I didn't try it, but I will try. But I think it'll be difficult to see the fluorescence of the organelles and then correlate that with the team image. but I will try. Anyway, I will try.
Yeah, good luck. Tell me how it comes, your results. And then we have a more recent microscope, this photon ion electromicroscope. I somehow have the bar from Zoom on my slide, so sometimes I cannot read everything. Okay, so this has been constructed in Melbourne in the lab of Alex De Marco. And as you see here, he put a light microscope next to the FIB column in a focused ion beam scanning electron microscope. And this as the idea that you have light microscopic control, or that you can check your cryosample, the fluorescence of your cryosample, to know where you are going to cut your lamella. And as you see here, the space is pretty dense. So they had to put the light microscope next to the FIB column, and they have a precise shuttle that allows to move the sample into the optical axis of the light microscope and then back into the optical axis of the FIB. So in the light microscope, they can then identify where to cut the lamella and then go into the FIB and cut the lamella there. Now, something really nicely Brazilian comes now. Oh, where is the slide? Here. Once when I was invited to give a talk in Buzios, there was also Christoph Kramer invited to give a talk in Buzios, and Christoph Kramer is, let's say, almost the father of super resolution microscopy. He was the PhD professor of Stefan Hell, who got the Nobel Prize in super resolution. So anyhow, we were in the same hotel in Rio and had regularly breakfast together. And one day he said to me, he was with his wife there, and one day he said to me, what do you think? Shall we go on some trips together? I said, why not? That's a good idea. And one of the trips was to go on the Sugarloaf. And while we were walking on the Sugarloaf, looking into the scenery, we were talking about light, he, me, electron microscopy, and then we had the idea, let us do something together. Because usually light microscopists don't like electron microscopists, sometimes also vice versa, but it's more that way. But Christoph said to me, oh, we are doing the same thing. We are just having other contrast instruments. And so I was telling him at that time, that was before the microscope of Alex came out, I was telling him, listen, it would be very nice if we could control our sample in the scanning microscope with light imaging, so that we can see the fluorescence, that we know where we are going to FIB, for instance. I mean, exactly the concept of Alex. And so, yeah, then we started. And with the help of Udo Birk and especially Johann von Hase, who is a theoretical light optic physicist, we made a patent, but we don't have the instrument, unfortunately, which is based more or less that we would have a ring similar as it is sketched over here around the either the electron lens or around the FIB lens. And then on a long distance that we can image the fluorescence. And the calculations of Johan showed that we could even get down to super resolution in whatever stat mode and so forth. And now we're still looking for some company who would be interested in realizing it. At the moment, it's only on paper. But anyhow, this was our story on the sugar loaf. Now going back to Lausanne, where I had very skillful and knowledgeable collaborator, Céline Lusser, who had to work on brain. We had a collaboration with a neurobiology group. And so she was absolutely fascinated by the Tokuyasu technique. So for her, it was not a single question that this will be done by Tokuyasu. So she developed the method I showed you on making native vibratome section of brain, then fix it in formaldehyde, glutaraldehyde, embed in sucrose, cut sections, and then mount the sections on electromicroscopical grids. And I'm coming back to that in a second. So here we have one neuron stained with fluorescein or lucifer, I think it was lucifer yellow by injection. And we can follow it. We can see here it in the white field image. We can see here the neuron in the fluorescent image. And then after the preparation, let's say Céline then cut out this area here. So this block, because there was the cell in the fluorescence, and that was mounted on the pin, and then impregnated in sugar. And then with normal wide field microscope, she was taking images in 10 micron steps. And then we could see at 80 micron, the sample came into focus and remained into focus till 240 micron. So we knew we have to remove something like 80 micron before we get to that cell. And for this, we adapted the method from Andrew Lees, who is now also in Melbourne, I think. We added a fluorescent stereo microscope to the ultramicrotome. So we could see the neuron here in the block so that we could nicely trim to the block. And then cut sections. What I'm showing here now is not that new neuron, but it was the other work we were looking at that was at astrocytes. So the astrocytes were labeled with GFP under a promoter that is only active in astrocytes, because this group wanted to know if neurotransmitters like V-glut and so forth, if they are also expressed in astrocytes, because they think, or their idea was that astrocytes are not only, let's say, nourishing cells for the neurons, but that they are also somehow involved in signaling. So we had this ribbon, like you see over here, was on such electron microscopical grid. We took high resolution fluorescent image. It was with an oil objective 1.4 NA. And then Céline did an immunogold labeling, and to prove the concept, she labeled against GFP so that we saw the fluorescent marker afterwards. Took a picture in the scanning microscope on a with a transmission detector, so that we could do STEM in the light microscope, in the scanning microscope. This is now a secondary image to show the grid. As you have seen, the grid has some markers here, the number 1, and then it has also a central point. So with the software, this map software, we could then indicate those markers, and then automatically the light micrograph image was overlaid to the electron micrograph image. And then we could find the cell back and then overlay the fluorescent image with the electron micrograph. So this way we could identify that this is a neuron cell nucleus, whereas these are astrocytes. And this was actually the extension here with the fully filled cytoplasm of the astrocyte I was showing you previously. And then at higher resolution in the astrocyte, we had GFP to prove that this is an astrocyte and that the V-glut label is in this astrocyte. Yeah, higher magnification. Then another problem where the correlative microscopy can... Yes?
Bruno, yes, can I ask a question about
Sure.
your previous slide? When you pick up the sections, the cryo sections, and what is the stability of the GFP after the fixation and the urinal staining? They still get well fluorescent after all these steps?
Very good question. I was not telling it. The fluorescence image we do in buffer. So that means the grids are after thawing the section on the grid. The grid is washed with buffer. That means the sucrose is removed, and then saline embedded it, let's say, in buffer. She had the buffer and then the cover slip on top of it, and then fixed with nail polish. And then she did the imaging. And afterwards, she disassembled this setup and did the immunolabeling, as you will see here, the washing buffers and gold label and so forth. And only then, down here, she did the embedding in methylcellulose containing urinal acetate.
Yeah.
So during fluorescent image was no urinal.
Yeah, so we take the light image before the processing for immunogold.
Right. Yeah. And then after the section here, after embedding in methylcellulose containing urinal acetate, we did not image in fluorescence anymore. So that has already been done.
Okay.
So Bruno, did you perform the light microscopy and electromicroscopy in separate devices?
Yes.
Okay.
Yeah. No, that there was a dedicated light microscope and a dedicated electron microscope. And at the beginning, we were talking about it. I was discussing with Celine if she would be interested in having the combined microscope, because it would have been possible because we were, at that time, we had money to buy a microscope. And then she said no, and actually in our case, at least, it was a good decision, because this way we had optimal imaging for light microscopy and optimal imaging for electron microscopy. So we didn't need to compromise. And I still think for the applications I'm thinking of, I still think that this is the best, the better method. I mean, for my projects at least.
Bruno, when
Yes.
you image the cells, you said that you use the scanning electron microscope in the STEM mode to make the image of the cells.
Yes.
Is that image that you are showing now?
Sorry, is this?
This is a stem image. Is it a stem image? That one that you are showing now?
Yes.
Yes, okay.
Yeah, so these are STEM images. They are taken in, actually they are taken in the FIP microscope, but only with the electron gun. And it had a special stem, a special holder where you could put the grids, and underneath you had then the STEM detector.
Ah, okay, perfect.
Yeah, yeah.
Thank you.
At that time, the map software was not available for transmission microscopes, but for scanning microscopes. And I was lucky enough that thanks to my friends at FEI, I could do, or we could do beta testing of the software. So many of these images we could already do before the software was released. So it also helped me to gain quite a lot of experience in, in using that software. Okay, now coming to another problem, that is insufficient gold labels. So this was a collaboration with people at the veterinary school of the University of Zurich. And they were interested in looking at a virus protein that was expressed in a cell. And now we know that all these structures here, of course, you could have expected, but now we know that all these structures here is the viral protein. And my colleague, Elisabeth Schraner, she was doing a normal, let's say, Tokuyasu labeling. So she had Lovicryl embedded samples, and that the immunogold, and then she got about this distribution of the gold particles. I mean, you probably will accept that I showed them with yellow spot, because you probably wouldn't see it underneath. And I tried to find all of them and tried not to cheat you. So that's a distribution of the gold. And you see there is some gold over here, but there is also gold here where you don't see these structures, and there's gold here where you don't see these structures. It's very difficult to decide whether this is now a real label or where it is a background label. And then Elisabeth said to me, but look, first I have to show this one, said to me, but look, in the fluorescence, we see it very clearly. I said, yes, I see. So the only thing what I can suggest to you is we do correlative microscopy. And going back now, this is maybe one of the reasons, because the gold particles are negatively charged. That's also why they can stay in solution. That's why they are colloidal. Because if they would be uncharged, of course, they would sink to the bottom. And if you add salt to the solution and neutralize the charge, then of course they sink. And here, just by looking at this factor, you see the larger the gold particle, by square larger the surface, and by that also higher the surface charge. So that you see that you increase with the gold size, you increase also the repulsion. So this can be one of the reasons. Another reason is also, we saw earlier already, I saw with measles virus, we saw with Tabak mosaic virus, that labeling of viral particle is with gold is really very, very low. Why, I don't know. Maybe it's because of the negatively charged nucleic acid, but I'm not sure if this is really the reason. Anyhow, so Elisabeth then came with fluorescent images of her cells, and which were on a grid, and with the grids we put them into the scanning microscope with the transmission detector. And then we overlaid the images. So for instance here, then we clearly see that this very dense structure and also this particulate structure is completely clear that this is a virus. But also in this area where we actually don't really see much separated structure from the cellular structure. Of course, it's a little bit different than this one here. We could then clearly demonstrate the distribution of the viral particle in this cell. Another way is here the work from. Yes,
I had one question. You are showing for us some correlative images that you use GFP labeling for fluorescence and good particles labeling for electron microscopy. We can do double labeling, perform labeling for fluorescence, use a primary antibody and a second antibody with a fluoropher, and use the sample for correlative using second antibody with gold particle labeling. Is okay for correlative microscopy?
Yes, you can do in that way. I will show you some results also. And this was actually already how do you say, this was labeled section, so this was not GFP, the rotavirus.
But in this situation, you can there is a competition between the fluoropher antibody, secondary antibody, with the gold particles antibody, and you can reduce the gold particles on the sample.
Yes, I will show you.
Okay, sorry.
No problem. I mean, thankfully to my colleague Heinz Schwarz, I do have exactly what you're talking about. It will be coming actually after Wanda Kukulski's work. So she was looking at the endocytic sites in yeast, and so she had two label, a green one for the protein at the endocytic site, and a red one for an actin binding protein. And so she prepared the cells by cryofixation free substitution, and added to the sample also fiducial, these fluorosphere markers, which she could see in fluorescence, of course, but she could also see them in the electron microscope. Now she was using them to correlate the electron micrograph to the light micrograph. And then she was looking at this place here where she had the endocytic site and the actin binding protein. And then you see that you indeed have invagination, some kind of endocytosis in the yeast cell. And she made quite a nice movie how this works, and I wanted to show it to you, but it refuses to show in my slide presentation, so I took it out. It's really very nice work. Then there is another possibility for the correlation, and this is infrared branding. Meaning that you are looking in the tissue, so I think this is also nerve tissue, if you have in green labeled nerve, and then they wanted to look at this area here, so they were indicating it or actually marking it with infrared laser, so they were burning a hole in it. And this infrared you can see in light microscope as a fluorescence, but you can also see it in the electron microscope. So here in the electron microscope,
Pessoal, microfone ligado. Pessoal, alguém está com o microfone ligado.
Nossa, não vou misturar com o show.
Okay, so you can see here the place where this area is, and with this, then you can target into it and find this branch, as you see over here, this branch of the neuron. And this is actual work we are doing actually now. So I Takahashi in the lab. The pictures are from last week, not this one, but the ones you will see afterwards. So this is really very fresh. So she has two cell types also in an organoid. The green one is a younger cell type, and the red one is an older cell type. So she made here the ER branding, infrared branding, which you see quite nicely in the fluorescence. And then again with the map software, which we have on that microscope, as you see here clearer, you see here the section, and then here is the cleft burned out with the laser. The section only goes to here, so here is no cells. And so we could overlay it and then see here the area with the green label. So these are the younger cells she wants to study. And here, for instance, are the older cells she wants to study. Here we have two areas, the older cells over here. So they seem to have a bit more vesicles, but as I said, this results from last week. So we don't know yet what we should really think of. So we have to work a little more to know. This would be the younger cells area. And just to show that this is also a possibility for a correlation, and I hope we will get soon some better results, and especially more, so that we can take conclusions. Now, the last part will be the correlative microscopy towards volume microscopy, and there are two ways we can do it. One would be, for instance, array tomography, and the other one would be some kind of serial block phase tomography, either using scanning microscope with diamond knife cutting, or what we were using is focused ion beam. So now we are coming towards the question of Victor. So that's there's, let's say, initial experiment to see how it works, if it works. So you don't. So for array tomography, we don't have here a real array. We only have 4 sections. So these are sections of trypanosoma, again. Made by Heinz Schwarz, and he came with the sections and the fluorescent images, which you will see maybe later on. And then again with the map software, I overlaid the fluorescence image onto the electromicrograph. So these are now backscattered images. So the sections are mounted on indium tin oxide coated cover slips, so on an electron conductive cover slips. And then, for instance, we were in the fluorescence, we were then using, selecting the group of cells we wanted to look at, and then took the electron micrograph. So we just used the fluorescence image to find the cell we were really interested in it, and then to guide us, and then we took the electron micrograph from that area. And now this is the label. It is actually a quadruple label. So we had for the trypanosomes, we were using as a primary antibody rabbit anti-variable surface glycoprotein antibody and the mouse anti-tubulin antibody. So primary. Secondary, we were using goat anti-rabbit 6 nanometer gold antibody and goat anti-mouse 12 nanometer gold. And as I have told you, I didn't show those pictures with, unfortunately, the pictures with which show it very clearly with the measles virus. They I left in Munich when I moved to Utrecht, so I unfortunately didn't take the pictures or negatives with me. Probably I would also not have been allowed to do so because it belonged to the lab. So yeah, that very beautiful image to show you what I'm telling now, I unfortunately cannot show you. So due to the bad labeling we have with the gold compared to the fluorescence, after the gold label here, we still have enough primary antibodies unlabeled where we can, which we can detect with the fluorescent antibodies, what you see over here. So first primary antibody, second the gold antibody, and then in the third step we came with the fluorescent antibody. So that's what we have over here. So we have tubulin in red, VSG in green. This is a DAPI stain. It helped very nicely to see the erythrocytes, which were not labeled, but we found them back in the electron microscope. And what you also see here is the nice holes I burned with the electron beam. So for us, the advantage was we knew which cells we were looking at. So we could afterwards, we could number the cell here, and then after could number the cell over here and knew exactly which one we were looking at. But this is also a little bit a warning for those people who always say, if you do array tomography, you can always revisit your section. You can always take images again from your section. You can, but you cannot, because as you see here, it's pretty damaged if you take a high resolution image. So it's only half the truth that you don't lose the section and can re-image. An argument people often use against the serial block phase imaging FIB or so on. Anyhow, so this was the cell we chose at that very moment in the peak. We see now the tubulin stained here. Here the tubulin of the flagella, what was it, 9+2. And then the variable surface antigen on the surface of the trypanosomes, but also in the flagellar pocket in here. And this thought brought us to the idea, why don't we use super resolution? So we were using super resolution together with Christian Wurm from Göttingen. Planck in Göttingen, and with super resolution, it's really nice, as you see here. Now the colors were changed. So here in red, we have now the variable surface antigen, and in green, we have the tubulin. Here is the flagella. We can almost see the tubules, the label of the tubules, and again, the flagellar pocket. And then in the electron microscope, it looks like this. There, of course, we see the tubulin very nicely. So under the membrane, the tubulin skeleton, we see very nicely the small gold. And we see that in this case, the gold label of the tubulin was a little bit less successful. So you see the density is really very small. And probably again, if we wouldn't see the tubulin directly, we might doubt if this label is really efficient. So going back to this image here, why don't we just combine super resolution with electron microscopy? Here it is. So if we combine super resolution with electron microscopy, we can actually use the fluorescent marker instead of gold. So this is again, this is another thing I would like very much like to pursue in the future, that for difficult to stain, difficult to gold label material, that we can do correlation, that we can use super resolution fluorescent image to stain, to identify the structure of interest on the electron micrograph.
Bruno,
Yes.
yeah, I have a question. Do you think it's with this evolving methods to do correlative, if you have a super resolution image like that, and you have the electron imaging in the SAM on the TEM, do you really need to use the gold marker?
No, then we don't need the gold marker anymore. So this is exactly because you see here that the tubulin is so poor in this case. I don't know what has happened, because in previous experiments the tubulin was really nice, yeah. But in this later experiment the tubulin somehow was not so convincing with the gold anymore. So here we did just to see if we can do a direct correlation of fluorescent and gold marker, but afterwards this gave then with this I got the idea, so why gold? Why can we not use the more efficient fluorescence as a marker?
Yeah, okay, because I was looking for gold secondaries to buy for the lab, and it was really difficult to find places to buy these gold secondaries now. It's really limited in the size and the types of animals that they made the secondaries. I don't know if they are extinguishing the gold secondaries. It's really difficult to find now. Wow.
Yeah. Oh, really? I mean, I didn't buy it in a long time, but usually I buy it from Orion in the Netherlands.
Okay, Orion.
Yeah, I mean, offline I can give you the address.
Perfect.
Just let me know and I send it to you.
Okay, thank you.
Yeah.
Bruno,
yes.
This image was captured, was acquired from a combined microscope with STAD and TEM, or you use two different microscopes?
Two different microscopes. So the STAD was done on an experimental setup in Göttingen, and the electron microscopy was done in Lausanne. So Heinz came with the sample and the pictures. I mean,
did you mark the cells to perform the overlay? Because you find the same cell and put the overlay in. How do you perform this with different microscopes?
I don't know if I can. Maybe I don't have it here. Yeah, more or less I can show it here. Wait a minute. Let's find this one. You see here is a flagella. So I was using 1 point here. So this software has let's say one option is to have 3 points. So I make, oh, wait a minute, can oh no, I thought I have drawing. Okay, I don't have drawing. So I put point number 1 here. So when I read in the fluorescent image, I have in the software, I have my electron micrograph and I have my light micrograph, like you see it here. So I have here my light micrograph and here my electron micrograph. Now I put point 1 here in the electron micrograph and then point 1 here in the, oh, it doesn't work, here in the light micrograph. And then I look for another clearly to be seen point. This is actually also clearly seen. Now you don't see it anymore because of the bleaching of the beam, but this was also one. So you can put this one and this one, and then we can, oh, these are also clearly be seen over here. So then I take this one as a third and this one as a third. And if these 3 points, then the software automatically overlays. So it turns the image, it translates it, and it also changes the magnification that it fits.
So the user software, is that Coresight software?
No, this is a map software.
Oh, okay, okay.
Yeah. Sorry, I'm sorry, Coresight also uses map software, yes, but you don't need Coresight to do the overlay.
Thank
But
you.
Coresight has the advantage that you can start the project already there and then read the whole project into the scanning microscope. But these were all done with individual pictures. So we had a stack of individual pictures, and I read them into the map software on the electron microscope and then did the overlay.
Perfect, thank you.
Yeah, you're welcome. Really good questions, because I only tell you half. Okay, so then there are, of course, towards ray tomography. We have here the atom tone, where you can collect maybe kilometers of individual sections. Maybe you can see them here. They are coming up. So there is the idea is to have a conveyor tape that is going into the boat of the knife, behind the knife edge, and then after the section is cut, it floats over, will be taken up by the conveyor and pulled out of the water. So you will get then a long ribbon, which you can then in sequence put next to each other for imaging. Or what also actually a very interesting system is this one. I don't know if you have ever seen it, but I was lucky to hear a talk from Thomas Dompier, who developed it. He made a dummy epoxy block, which contains 2 colored fluorescent beads and magnetic particles. Supermagnetic nanoparticles. And this dummy block he glues onto the block of his sample where he's interested in. And then he can randomly cut sections. He just cuts sections. They swim then on a huge knife boat. Actually, it's so huge, it's about this size, because it can take up a silicon wafer disc. You know, they are about this size. So this is lying here in this boat. So the sections are floating on the water, and then he has a magnet, which somehow it turns, and it collects the sections, centers them in the middle, and then they are lowered onto this silicon wafer, as you see over here. And then you have fluorescent beads magnetic beads here in this part, and this part is your contains your sample. And he claims with the small changes you're having from section to section. So you see you have here a nice pattern. And then when you take the next section, you still have almost the same pattern, but maybe some of the fluorescence gets thinner because you are almost cutting through the beads. Other new ones comes up. And with this and the special algorithm he developed, he can then identify the section sequence. So even if it looks completely crazy here and you have no idea which section is 1 and which section is 2, with his software he can align them like you see over here. And once aligned, he can align the images he's taken and can make the 3D reconstruction. It looks really cute. The instrument itself was a little bit above my budget when because I was thinking I should buy it, but yeah, unfortunately I couldn't. Anyhow, another method was developed by Irina Kolotuev, who was before in Rennes in France, before in Strasbourg, and then joined my lab in Lausanne. And she also developed her way of doing array tomography. Here we see, if you are really careful, really skilled, how you can take up sections on a whole grid, electron microscopical whole grid, the 1 by 2 millimeter grid. She then developed together with Helmut Knagge from Diatom this knife here, where you can put a piece of a silicon wafer on a little stand, so it lies like this, and then of course float the knife with water. I will show later on. And then if you have sectioned the ribbon, you can pull them together and then lower the water level so that they attach on the silicon wafer. Or you can also use a glass slide, but she preferentially uses the silicon wafer. And then you see, of course, here as a comparison, this is our electron microscopical grid over here in comparison to the section you can accumulate on a wafer. And of course, the electron microscopical grid, if you touch it with a forceps, then your film is broken and your sections are gone. Whereas on the silicon wafer, it's far more stable. You can do more stupid things without really losing your data. You just need to know which section is the first, which is how it was oriented. So you shouldn't mess up the orientation. And this is now images also. This movie didn't want it to run on my presentation. I don't know why. It was the first time. Anyhow. So she is sectioning ribbon and then make, let's say, more or less coarse alignment above the wafer. And as you see here, there is a tubing down here. With this tubing, she can slowly lower the water level, like you see here. And finally, you have still just a little thin water layer on the wafer. And this allows you then to do the fine alignment. And then you let it dry. And then it's ready for inspection. So you can do now a fluorescent label on it if you want, but you can also just do volume microscopy in trying to find the area of interest and then take images of every section to make the 3D volume. And what's really very nice, you should show here, what's really very nice, she had developed a new strategy. So she is not going to look from here down here to find the sample of interest. If, for instance, she has no fluorescence, if she has fluorescence, she sees, of course, directly which ribbon has her object of interest. But if she doesn't have the fluorescence, she cross-examines. So she looks here, this section, oh, nothing on, this section, nothing on, and so forth, like you see now over here. And then suddenly you get into the section where you have your sample. And once there, she goes left, right to take the images for the 3D volume. This saves quite a lot of time. And then, yeah, here you have the fluorescent image if you do fluorescent. So I think this was with GFP. And then the corresponding electron micrograph, and then you can stack them in 3D. And now we're going almost to the end. Another collaboration we had with Kori Minehira. She was at that time also at Lausanne University. She, now I forgot even the project, but I think it had something to do with special protein involved in mitochondria organization. So she knocked that protein out with iRNA, and in that probe she added also fluorescent probe, so you could identify the cells that were knocked out. So that were the fluorescent cells, and the non-fluorescent cells were normal cells. And of course, if you want to check what this protein does, you should not image a normal cell by accident, but you should image the knockout cell. So that was one kind of correlation you could do. So you had the fluorescent image, and here we looked at the surface of a block prepared for the FIB. And then you could overlay the cell, and then you knew this is the cell we have to go to FIB and take images. And finally, another project was together with a group in Paris with Florence Niedergang. She had macrophages that are infected with HIV and Salmonella. Salmonella is in red and HIV is in green. So we transferred, let's say, the fluorescent image onto the electron micrograph. And no, this is not an electron micrograph. This is a light microscopic image, but with this we could identify the cell and then look at this cell in the FIB. So here are the given dimension of the volume we were getting. So it's 30 micron in width, about 20 micron deep, and 16 micron height. And as you see here, there were quite a few sections, 2000, and at 100 angstrom or 10 nanometer thickness. And this gave us then the distribution of the Salmonella in red. And these were the Salmonella that were seen in the fluorescence. But afterwards in the electron micrograph, you could also see Salmonella that was already partially digested by the cells. So we could find that in addition. And this here was the area with the HIV virus. And that's then the video. Is it? It's not running. Okay. Sorry, I cannot show you the image. It was running before the lecture here, but I don't know what has happened. Okay. So with this, I'm coming towards the end, and I hope many of the people I mentioned in the turn of the talk, and here it's just a selection, they are not all the people who were involved. So let's go maybe in time sequence. Utrecht University, Sasha and Hans were from physics, so they made the fluorescent microscope for the electron microscope. Mattia, she did the experiments, and this was in the group or in the department of Arif Clay, who was always a great supporter for whatever I wanted to do, whatever ideas I had. So he was really very important in my career. At that time, I had also a lot of help, even almost up to now, from Ben Lich, Matthias Langhorst, and Cliff Mattison for the map software, especially from FEI company. Maybe I even should have mentioned the Max Planck Institute in Tübingen and Göttingen earlier, because Heinz and Jörg are important people for this work since the 80s, so really very long time. And Daniel Jans and Christoph Wurm, they were involved with the STED experiments from the trypanosomas. The group from Zurich, the rotavirus, with Elisabeth Schrauner and Andrea Leimbacher, Anita Meyer. My former team in Lausanne, Céline and Irina, mainly for the correlative microscopy, Caroline and Jean more for FIB. And Willy was the patient person who did the modeling of the cell. Unfortunately, I couldn't show you because the film didn't run. And here my collaborators at the OIST, who are involved in the correlative microscopy projects. And with this, I finish. Thank you very much for all your attention and questions. And if you have more, please do so.
Hi, Bruno. Thank you so much. It was such a wonderful talk. Really, really, really good lecture. I made a lot of notes, and I have already a lot of ideas to apply to my work. And I have just one more doubt is about when you collect the samples in the top of the silicon wafer or on a cover slip. Did you make any other metallization process to look at the SEM?
No, I didn't.
No.
I think the silicon wafer, you should, I'm not 100% sure, but I think you should plasma clean it so that it's more hydrophilic for better touching the sections. But we did not do any coating.
Okay.
Yeah.
Perfect. Really, really good.
Bruno,
Yeah.
thank you for
Yes.
that talk.
Yeah, you're welcome. Thank you. As I said, thank you for the nice invitation. I'm happy to join.
I have a question
Yes.
about what we can consider as a correlative analysis or correlative microscopy. I asking this because nowadays we can track elements from periodic table in our biological samples using X-ray microanalysis.
Yes.
To consider as a correlative microscopy, just we need to use different techniques as a light microscopy and electron microscopy, or we can consider if we put together a track not as a quantitative analysis but a qualitative analysis, and we can track these elements inside our samples. We can consider this as a correlative microscopy too.
Yes, I would. Yes. I mean, I didn't show, but when I was in Lausanne, we also did correlation between electron microscopy and nanosims. So, which is very similar to what you're saying. So, with the nanosims, we were also looking at elements. at isotopes actually. And if you use X-ray, the way you're saying, you're doing the same. So actually, let's say you label with the X-ray signal the area you are interested in. So whatever, I mean, correlation, probably it's it's any kind of combining imaging. You could even do correlation with, I would say, biochemistry, so that you use an imaging, let's say, an imaging method to isolate special structures you then analyze in biochemistry, or what, this kind of things.
Perfect.
Or if you use those dissecting microscopes, you know, that you have a section, a tissue section, and then as an example, you label it with fluorescence. You label your cells of interest, and then with the laser you cut them out, and then you can, with this instrument, you can flip them out then in an Eppendorf tube, and then you can do whatever RNA analysis, PCR on it, and these kind of things. I guess with correlation, you can almost use any kind of idea you're having to correlate.
Two things, okay, two different things.
Yeah.
Thank you, Bruno. Pessoal, alguma pergunta? Podem fazer em português.
Bruno, thank you very much for your talk. It was excellent.
Thank you, Miriam.
Really a nice view of the correlative microscopy, and you showed many strategies to get it. It was fantastic. I have a question. In fact, it seems to be a little delicate to transfer the grids from to washing the fluorescence microscopy, and later on you transfer it for the electron microscopy. Is it an easy process? It seems that it will be a little damage. It can be damaged in the grids. How do you do it? Can you give us just one tip?
I mean, it can damage, and I have to, I don't know if I can give you much a tip. I just can tell you, hire Selin. She is so skillful, but I guess you will find this kind of skillful people also near you. So the main point of damage, to my opinion, is after when you want to disassemble the as it called, the microscope slide and the cover slip on top of it. There, when you are too cruel, then in lifting up with shear forces, probably you can damage the film of your grid. I guess that's the most crucial point. The other points are okay. They are just, let's say, normal electron microscopical handling. I mean, with all, you have to be a bit careful, especially that you don't sting your tweezers through your sample. But I guess every electron microscopist does this quite well.
All right, thank you very much.
Yeah.
Very nice talk.
Thank you so much.
Bruno.
Yes.
I was you said in your first slide that you doesn't have a lot of experience with live imaging, but I heard that there are some electron microscopes, transmission electron microscopes, that has now some kind of special chambers that you can imagine with liquid, and you think this is a good way to do some type of correlative microscopy inside of the electron microscope?
I cannot say much about it. The only thing what I have seen up to now is for me the resolution is not good enough.
Okay.
I mean, the resolution is not on electron microscopical level, and it's probably my ignorance, but at the moment I don't see a biological question you could solve with such an environmental chamber.
Yeah,
so it's yeah.
I have for example about my project. I work with some macroalgae, marine macroalgae. So they have their cell wall mineralized with calcium carbonate. So we have some questions about climate change. For example, if you have higher pressure of CO2 on the seawater, maybe they will not mineralize the same crystals or the same amount of crystals. So if you have like a chamber that you could manipulate the CO2 level, for example, at the seawater. I don't know if I can put seawater on an electron microscope, but
I guess in such an environmental
like,
chamber you can.
Yeah. So this is a question that I was trying to see if there could be a good application, for example.
For me, the question comes more: how long do you want to keep your CO2 level? I mean, I think you should keep it longer than you usually would do for observation in the electron microscope. I mean, we do with collaboration from Ryukyu University. That's why this is here. We are looking at actually very similar thing, and this is how diatoms react upon different CO2 levels. So how the structure of the chloroplast changes.
But then you maintain in the experiment like in a aquarium something, and then you transfer to the electron microscope to see the differences.
Yeah, yes, they have it. The diatoms are in a cell culture bottle. Okay. In a special environment, special oven temperature and CO2 environment. And then what we did the most successful in structure was we then did high pressure freezing and freeze substitution and EPON embedding. But my colleague Atsuko Tanaka, she also did chemical fixation. That for me doesn't look so nicely, but we had some difficulties with our high pressure freezer. But the high pressure frozen really look very beautiful.
And then they analyze this at different times.
Yes, I mean it's on the way. We have not done. We have not. Where I was involved, we have not analyzed so many yet. We predominantly had the wild type, and one of the wild type normal condition, and one with a higher CO2 level. So this is really still ongoing. Yeah.
Nice.
Yeah.
Thank you.
You're welcome. I mean, I guess in your case, probably you also have to keep them for a couple of days in that environment.
Yeah, I was maybe my idea is trying to do with spores that they doesn't have the cell wall impregnated with calcium carbonate yet.
Yes.
And then if I want to see if they have some kind of difference in calcium incorporation or different calcium polymorphs mineralization or something like this.
Yeah.
That's probably something that I can look at a short amount of time maybe.
Yeah, I see.
But thank you again.
Welcome. Thank you.
Bruno, the students are congratulating you for the talk in the chat.
Oh, thank you.
Everybody is saying that was amazing. It's a wonderful class. And Luis Alberto asked, which was the type of filament used in the SEM images?
Schottky field emission gun.
Emission gun. Okay. Perfect.
Yeah.
Okay. People, anyone have more questions? Victor, Miriam?
Oh, for me, it's good.
Okay,
Oh,
so
fine.
I think we can unfortunately finish the lecture.
Mm-hmm.
Hopefully we can count on you on on other lectures because it was really, really good. You brought to us a lot of new information and historical background that was really, really important for the students because we usually don't talk about history. So history, it's important to understand why we do things the way we do. So I think it was really good, this part.
Thank you very much. I was only discovering the history in time. When I was writing a paper, so I was going back and trying to find more information. So it's interesting. I mean, I think I even found an article of Hoke, the inventor of the two-compound light microscope from 16 something. It's amazing what you start to find nowadays on the internet when you really dig in, when you are interested in this, getting further and further.
Yes, exactly. I was like, oh, 60. So what's guys were doing correlative microscopy, dual microscopy in 60s. It was really, really amazing.
Yeah.
So I think we can finish it. So maybe you are tired. Is your time to sleep?
It's okay. Still today.
Almost midnight.
Yes,
Almost
right.
midnight. So thank you so much, Bruno. It's such a pleasure to hear you every time you speak. So you are welcome in Brazil. Please, when you came here, contact us so we can.
Sure, I will. It would be nice to meet you all in person again.
Me too. Thank you so much.
Yeah, thank you very much. Caroline, Victor, and Miriam, thank you so much.
Thank you. Okay. See you soon.
Yes, bye-bye.
Bye-bye.
Bye, Bruno. Thank you.
Bye.
Pessoal, alguns avisos. Eu recebi mensagens para poder colocar mais 2 pessoas como aluno da disciplina. Não esqueçam de dar a presença no site, já está liberado para vocês dar a presença lá, tá? Eu já dei a presença de ontem não estava liberado, então dei a presença de todo mundo ontem. Se por acaso eu esqueci de alguém, me avisa ou por e-mail, tá?